All right, hi everyone. Welcome to lecture 10. This is going to be a relatively light lecture. I'm just going to go over two more tests that help determine convergence and divergence of infinite series. And hopefully at the end, I'll be able to kind of tie up some loose ends, I guess, cover a couple tidbits of things that I think I might have neglected in the last lecture. So we'll see. So for the first part here, I'd like to talk about the integral test. And this one, it's going to be a little bit weird because, this class has placed a great deal of emphasis on, building a theory from the ground up and doing everything rigorously and making sure that everything we say follows very precisely from the things that came before. And the integral test is going to buck that trend a little bit. I'll sort of, when we get to sort of like talking about the examples and stuff, I'll say what I have, my thoughts about, sort of what the value of introducing it now and kind of the relationship it should have to the rest of the material, at least from now until we actually define what integrals are. Right. But for now, let's just kind of, pretend that we know exactly what integrals are and we're perfectly comfortable thinking about them and talking about them. And we're just familiar with them from calculus. So the basic idea, okay, so the idea is if an equals f of n for some, suitably well-behaved function f, and I'll talk more about what that means later on. But right, in a lot of cases, it'll be like when we define, the terms an, we'll have some expression, we'll have like a formula here in terms of n, and that formula, literally, you can think of it as sort of a definition of the function f. If you kind of think of n, if you replaced n with x and think of it as like a continuous variable instead, you could use that function, at least in a number of cases. Not in every case, we'll see. Yeah, for now, if we think of an as being the values of some function f, as long as f has the right properties, then the sum of an exhibits the same behavior as the integral from, let's say, I don't know, a to infinity. Of f of x dx, okay? So the reason I say a here is just because depending on how these things are indexed and depending on the function f you choose, you might want to take this integral from some other point on, out to infinity. But what really matters is like this integral's behavior is dependent only on basically the asymptotic behavior of f and not really, we don't really care about what's happening near a, as long as a is chosen correctly. Okay, so before I actually describe the principle here of why this is true, which is not very complicated, to be honest, and we're not really going to rigorously prove anything here because, like I said, we haven't actually defined what an integral is. But I would like to give you just like a couple motivating examples. Well, for one thing, the integral test is sort of like one of the biggest motivations for us to introduce it now is because it gives us, this is like the most sort of common or straightforward way of showing so the integral test can tell us that the series of 1 over n to the p from n equals 1 to infinity converges for p greater than 1 and diverges for p less than or equal to 1. And this is kind of important just because these series, it's useful to sort of be able to take for granted which ones converge and which ones diverge, because we end up using them a lot in things like the comparison test and stuff like that. All right, sorry, I had to make an edit to make sure I was making these integral calculations correctly. But so basically, the reason the integral test tells us that this converges when p is greater than 1 and diverges when p is less than or equal to 1 is because if we look at the integral, right, the integral from, say, 1 to b of 1 over x to the p, at least assuming p is not equal to 1, right, then we get negative 1 over p minus 1 x to the p minus 1 evaluated at b and 1, which is 1 minus 1 over p minus 1 b to the p minus 1. Okay, so as you can see, this approaches 1 if p is greater than 1 as b approaches infinity, right? Because then this number here is positive, so this whole thing just goes to 0. But it approaches infinity if p is less than 1. Because if p is less than 1, this is actually negative, so this entire thing becomes positive, and then b, since this exponent is negative, it's actually, this expression goes to infinity as b goes to infinity. So this is essentially why these sums converge and diverge under these circumstances, except in the case that p equals 1. So if p equals 1, then we get obviously log of, you'd get log of x evaluated at b and 1. So log of b minus log of 1, which is 0. So just log of b, and then that also approaches infinity as b approaches infinity. Okay, so at least once we know the integral test, this reasoning will actually tell us that, according to the integral test, these series converge when p is greater than 1 and diverge when p is less than or equal to 1. Okay, so let me just kind of like motivate the integral test a little bit. So because there's sort of this relatively simple justification for it, but I think it's also interesting to look at a couple specific examples. So if we consider the series 1 from, let's say, k equals 1 to n of k times k plus 1 in the denominator, this is kind of a very common example of something called a telescoping sum. So what's interesting about this series is that it's possible to write a formula for the nth partial sum, which is what this represents, obviously. The nth, this is the nth partial sum of the infinite series, right? If I just replaced n with an infinity here. So it's possible to write a formula for this in terms of n, because it turns out that this is equal to, the expression inside is just equal to 1 over k minus 1 over k plus 1. So this is just 1 minus 1 half plus 1 half minus 1/3 plus 1/3 minus, and so on, until you get a minus 1 over n plus 1, right? Because we're going up to n. So this is just 1 minus 1 over n plus 1, because all the terms inside cancel out. And what I want you to consider is that these terms here are almost the same as like 1 over k squared, right? The only difference is that there's just an extra k term on the denominator. But remember, as real analysts, we kind of only care about what the sort of dominant asymptotic behavior of this series is supposed to be. So we kind of, in our minds, we kind of think of this as being fundamentally similar to the series of just 1 over k squared, right? And if you go back over here and look at the formula for this integral, right? If p was 2, right, the integral of 1 over x squared from 1 to b, let's say, would be 1 minus 1 over b, right? And look what we have here, 1 minus 1 over n plus 1. That's pretty close to 1 minus 1 over n, right? So what I'm saying is the integral from 1 to b of 1 over x squared dx is 1 minus 1 over b, unless I made some arithmetic mistakes, which hopefully I didn't. So if you compare these formulas, they look kind of similar. And that is sort of, telling us that really there is a relationship between summation and integration, that when you take sums of certain types of, formulas, when you have a formula for the terms, that the value of the sum is actually generally somehow asymptotically the same as what you'd get by just taking that expression and integrating it with respect to whatever the index is or something like that. Okay, there are other formulas that you can look at, like something like the sum of k equals 1 to n of k, for example, is just equal to n should be n times n plus 1. It's either n times n plus 1 or n times n minus 1. I think it's n plus 1. N times n plus 1 over 2, right? So here, and then on the other hand, we would have that the integral from 1 to b of x dx, well, let's say from 0, I don't know. The only reason we're using 1 over here is because this has a pole right at x equals 0, but we might as well start from 0 in this case. This would be, 1 half b squared, right? So there is some similarities here. And that's kind of one angle on why the integral test makes sense. One more kind of interesting example is actually, if you look at the harmonic series, one of the classic ways of showing that the harmonic series diverges is to write out the terms and then say that this is greater than or equal to 1 plus 1 half plus 1 quarter plus 1 quarter plus 1/8 plus 1/8 plus 1/8 plus 1/8. There's a plus 1/8 here, plus, and so on, right? So then basically what you do is you take groups whose sizes double each time and then replace them. So you take the first one, the second one, oh, except for the first two, and then like the next 2, and then the next 4, and then you take the next 8, and then the next 16, and so on. And you replace each of them with like the smallest term in that group. And then each group ends up adding up to 1 half. Now, if you look at this, the value of this, the value of the partial sums here are basically going up as the logarithm of at least the base 2 logarithm of n. And the reason for that is because if you just think about it, right, the fact that you have to take exponentially more and more terms to get the same constant increase, right? If we double the number of terms here, we just basically add a half to the value of Sn. And that's the same behavior you'd get from the logarithm up to some kind of a constant factor, okay? So maybe it's like 1 half log, 1 half times the logarithm or something like that. I'm not trying to be really precise here, but basically there's a sense in which, so maybe not, instead of this one, maybe I'll use this other symbol of like asymptotically being related, right? So that's actually, related to the fact that the integral of 1 over x dx, the indefinite integral, or at least the definite integral from, say 1 to b is log of b. Okay, so basically the partial sums of the harmonic series do increase logarithmically, even though it's hard to actually write a formula for the exact partial sums. They do increase logarithmically, and that's related to the fact that the integral of 1 over x is the logarithm. So with these examples out of the way, let me just kind of show you sort of the picture. There's a picture, kind of a pictorial proof, okay, of at least let's look at the cases of the harmonic series, the sum of 1 over n and the sum of 1 over n squared. So the integral, and then you'll get the principle. So the integral test for the sum of 1 over n, right? What we do is, now I'm going to make a little cut here so I can draw a picture. Okay, so I've sort of drawn a diagram of the graph of the function f of x equals 1 over x as like a continuous function of x, and then also these rectangles which represent basically terms of the series of the harmonic series, right? And then within each rectangle, I've put the area of that rectangle, which is just equal to the height of the point on the left, right? Because the width of each rectangle is just 1. And so the height is just equal to the value of f at that point. So this is f of 1, which is 1, f of 2, which is a half, f of 3, which is a third, and so on, right? So each rectangle is, the area of each rectangle is one of the terms of the harmonic series, right? And so in the picture, the red area, which kind of is overlaying this green area, right? The red area is equal to, yeah, I guess maybe it's not super obvious that they're overlapping here, but this is supposed to be red on top of green. So the red area is equal to the, let's say a partial sum. So from k equals 1 to n of 1 over k, something like that. And then the green area, which is sort of inside here, doesn't look super green, I guess, but the green area is the integral from 1 to, and now, so if we're trying to compare the sum from k equals 1 to n, let's think about this, right? Let's say from k equals 1 to 3, right? We would want the first 3 rectangles. Now, as an integral, the green area in that part of the graph, right, actually extends all the way from 1 to 4. So actually this integral, the integral we want to compare to this is actually the integral from 1 to n plus 1 of 1 over x dx. So what we're saying is that the sum, in this case, the sum from k equals 1 to n of 1 over k is greater than or equal to the integral from 1 to n plus 1 of 1 over x dx, okay? And then the thing is, we know how to compute this. This is just log of n plus 1, right? So this approaches infinity, which forces this to approach infinity as well, right? So that's the idea of how the integral test applies to the harmonic series, or as you can probably imagine, many series whose terms are given by the values of some function which you know how to integrate. Okay, so I'm gonna show you how we can use it to show that certain series converge. So like the series of 1 over n squared. I'm gonna modify the picture a little bit. Okay, so now we're gonna consider this as the graph of the function f equals 1 over x squared. And what we're trying to do is now, because we want to show, oh, sorry, this is n squared. We want to show that this series converges, right? So as with the comparison test, remember the philosophy is that for divergent series, we want to bound them below by something that we know diverges, right? But for convergent series, we want to bound them above by something that we know converges, right? So here, what I've done is I've kind of shifted all the rectangles over. Now we're only using rectangles that meet the curve at their right endpoint. So as you can see, this first one is actually shifted all the way over towards 0, and then the second term is starting from x equals 1 and going to x equals 2, and so on. And so then basically, if you look at this picture, what you can see is that the green area, which still represents some kind of integral, is now bigger than the red area. And so, and one thing I've done is I've separated the first term of the series from the rest of them, because we don't want to, if we did an integral, like, so we want some integral of like 1 over x squared dx, right? And if we made the integral go from 0 to something, then that would be bad, because sure, this would be bigger than this, but the problem is this becomes infinity if you actually take the integral all the way from 0. So it basically gives us no information. And remember, to show something converges, we only really care about what happens, what happens for large values of k or n or whatever, right? We don't care about what's happening at the beginning. So what we're going to do is we're going to keep taking the integral from 1, and then we'll just take it from you know, if we take the sum to go up from k equals 2 to like n, the integral that stops at the same point on the x-axis as that sum will be the integral from 1 to n itself, right? So like if we want to compare an integral to the sum from k equals, or 1 plus the sum from k equals 2 to like 4, then we want to take the integral from 1 to 4, right? Because the n equals 4 term is right here. So if we set things up this way, what we can see from the picture is that 1 plus the sum from k equals 2 to n, aka, well, really, I guess we could just say the sum from k equals 1. So this is actually still the sum from k equals 1. Let's just make this be the sum from k equals 1 to n of 1 over k squared is less than or equal to 1 plus the integral from 1 over n, or sorry, from 1 to n of 1 over x squared dx, which ultimately is less than or equal to 2, I guess, if you want. I think that's what it approaches as n approaches infinity. Now, of course, remember, this does not tell us that the series as n approaches infinity approaches 2. We know it doesn't. We saw, well, we didn't prove it, but I told you before that this series eventually converges to pi squared over 6 when n approaches infinity. So again, this test is not meant to compute any values. The integral will not give you the value of the series, almost ever, okay? But yeah, so you can see that by sort of doing things using the right endpoints instead of the left endpoints of the rectangles, touching the graph, we got information in this case about a convergent series. One thing that might be a little bit confusing is like, okay, what would happen if we actually used the right endpoints for the harmonic series instead of the left endpoints, right? What would that tell us? So what if instead of, hold on, let me make an edit real quick. So if we go back to looking at 1 over n, right, the harmonic series, and pretend that we use the right endpoints instead, right? So why doesn't this show us that the harmonic series converges, right? I mean, we've bounded it above by something. Okay, but see, let's look what actually happens, okay? So the bound we get, the inequality we get is something like this. The sum from k equals 1 to n of 1 over k is less than or equal to 1 plus the integral from 1 to n of 1 over x dx, which is 1 plus, log of n. Okay, great. So the partial sum is less than or equal to 1 plus log of n. Now, let's think about what happens as n approaches infinity. As n approaches infinity over here, this expression approaches infinity. So what does that tell us about the partial sums? It tells us nothing, right? Actually, this is completely useless because if you know that something is less than or equal to something that goes to infinity, that just doesn't tell you anything about that. Anything is asymptotically less than an expression that, less than or equal to an expression that goes to infinity. Well, yeah, roughly speaking, right? So we got no information from this, and as well we should, because the series actually diverges, so we should be trying to go from the other way. We should be trying to show it's greater than or equal to something, okay? So that's why we choose the endpoints the way we do in the integral test, is to try to, either show convergence or show divergence, as the case may be, right? A series is only ever going to do one of those two things. Okay, so with that, I just want to, actually, yeah, I'm going to call it for this video. And then in the next one, I'll talk a little bit more about sort of the philosophy here and how you should what your attitude should be towards the integral test. So yeah.